Hey students, here we've got some inverse stuff and then some logs and then some exponentials. So the first thing we need to think about is that this is talking about finding the inverse and then finding the derivative of that inverse. And you might recall from Algebra 2 that to find the inverse, what we're really doing is we're switching your x and your y values. So this becomes x is equal to 2 f of x and then plus 2. To get f of x by itself, we're minus 2, so x minus 2, and then divide by 2 to get f inverse of x. So what we did here was we switched our x and y. I guess you could write this as f inverse. And what we got was, it's really 1/2 x minus 1, which is f inverse of x. And if I wanted the derivative of this, that would be 1/2, because that would be the derivative of this function. I'd also like you to notice that the derivative of the inverse is equal to the reciprocal of the derivative of the original function at a certain point. And this was just a line, so that comes a little bit easier. That might predict for this one that we'd have 1/3 is our derivative. Let's see if that holds true. So let's find the inverse. So we've got x is equal to 3 f inverse of x plus 2. We get x minus 2 divided by 3 is equal to f inverse of x. And when we do that, that's going to be 1/3 x minus 2/3. And the derivative of 1/3 x is going to be 1/3. That's what we predicted. Might be not so easy for things that are not linear, so let's kind of see what's going on here. Same type of thing. We're going to do x is equal to negative 2 f inverse of x squared minus 2. So x plus 2 divided by negative 2 square rooted. We're talking about x is greater than 0, so we're going to do the positive square root is equal to f inverse of x. So the derivative of this, so happy to do this, is going to end up being 1/2 square roots of, that's going to be negative 1/2 x minus 1, and then times the derivative of the inside, which would be times negative 1/2. Yuck. But that's that derivative, which does not look as clean as dealing with linear stuff would have been. Okay. For this guy, we've got x is equal to the cube root 2f inverse of x plus 3. That becomes x cubed. Minus 3 divided by 2 is equal to f inverse of x. Taking the derivative, that would be 1/2 times 3. So 3/2 x squared. And then the other part zeroes out. And that would be f inverse of x prime. About my least favorite notation in the world has to do with inverse stuff. Next up, we have some derivatives of inverse trig. And the way that we did this was by setting up some triangles and trying to figure some things out. The first step was always to try to rewrite this not in terms of an inverse trig thing, but a normal trig thing. So that's going to be sine of y is equal to 5x to the 4th. I like kind of doing the calculus-y stuff first and then doing the picture, but if you'd like to do the picture first, that's fine. Put an arrow here to indicate this is where we're going to make our picture from. But we know we need to get y prime, because that's what we're trying to find, the derivative of this thing. And that's going to be cosine of y times y prime, or dy dx. And on the right side, we've got 20x to the 3rd. Okay, Getting y prime by itself, we're going to have 20x to the third, and that's going to be divided by cosine of y. Now, the reason that we need a picture is that we don't know what cosine of y is, so we're going to use our understanding of our triangle trig to figure that out. And I've got an angle of y, because we know that sine y is 5x to the fourth, that's my opposite, divided by 1. The key here is that if I wanted cosine of y, I need an adjacent thing. I'm going to use the Pythagorean theorem. Hypotenuse squared is going to be 1. And I'm just going to write this as 5x to the fourth squared. And I take the square root because I'm trying to get just that side, not that side squared. Okay, so cosine of y then becomes 1 over, sorry, I was doing this upside down, adjacent, that's this guy, divided by the hypotenuse. So that's just the square root of 1 minus the quantity 5x to the fourth squared. Which means that y prime is equal to 20x to the third over the square root of 1 minus 5x to the fourth quantity squared. I'd also like you to notice that the thing on top is the derivative of this lovely thing inside the parentheses there. I wonder if that's a chain rule thing. Oh, wait, it is. Okay, same thing for number 6. I'm going to rewrite this as cosine of y is equal to 3x to the fifth. And remember that I need to deal with that in a minute with a triangle. Derivative of cosine of y is going to be negative sine of y times y prime. And derivative of 3x to the 5 is going to be 15x to the 4. Getting y prime by itself, because that's what we're trying to do here. And we get 15x to the 4 divided by negative sine of y. We need to know what sine of y is, and for that we're going to go make a triangle. I've got cosine of y, so let's put a y angle in. And cosine is adjacent, 3x to the 5 over hypotenuse of 1. Sine would be opposite over hypotenuse. So we need to do the Pythagorean theorem to figure out this last piece. It's going to be the hypotenuse squared, which is 1, minus the adjacent squared, 3x to the fifth, and then squared. That means that sine of y, oh heck, I might as well do negative sine of y, is going to be negative the square root of 1 minus the quantity 3x to the fifth squared. That means that y prime is going to be 15x to the fourth divided by negative the square root 1 minus 3x to the fifth squared. All right. Next problem. We've got cosecant inverse of x to the fifth. I'm going to do the same thing that we just did before, and I'm going to write this as cosecant of y is equal to x to the fifth. I know I need a triangle. And the derivative of cosecant is going to be negative cosecant y, cotangent of y, and that's going to be times y prime. Derivative of x to the fifth is going to be 5x to the fourth. Okay, to get y prime by itself, it's going to be 5x to the fourth divided by negative cosecant of y cotangent of y. So we need to make a triangle here. I made not much room over there, so I'll do this down below. Cosecant is the reciprocal of sine, so it's going to be hypotenuse over opposite. That means we're going to have x to the fifth over 1. And it means that our adjacent side is going to be the square root of x to the fifth squared minus 1 squared. Okay? Cosecant of y, well, we already have that. That's x to the fifth. Nice. Cotangent of y is going to be adjacent over opposite, which is this guy over 1. So square root of x to the 5th squared minus 1. Okay, plug stuff in. And we've got 5x to the 4th up on top. And on the bottom, we got negative x to the 5th, which we got from the beginning of the problem, times the square root of x to the 5th, all squared, and then minus 1. That's it. It's kind of gross, kind of messy, but we get to the same type of thing. Same thing's going to be true for number 8, which deals with secant. I'm going to make some nice little barriers here. So we were starting with secant of y is equal to 5x to the 4th. If I take the derivative, we get secant of y tangent of y times y prime is equal to 20x to the 3rd. Y prime by itself, we get 20x to the 3rd divided by secant of y tangent of y. We already have secant of y from the beginning. We need tangent of y, and to do that, we're going to make a triangle. Secant is going to be hypotenuse over opposite. Hypotenuse over adjacent. It's the reciprocal of cosine. So we're going to have 5x to the 4th and 1. And then this last side is going to be 5x to the 4th squared minus 1, and that's inside a square because of the Pythagorean theorem. Tangent is going to be opposite over adjacent, which means that this lovely square rooty thing is going to be tangent. So y prime would be 20x to the 3rd, and then we said that secant of y was 5x to the 4th, and tangent of y is the square root of 5x to the 4th squared minus 1. And that's it. Okay, we're going to keep going with the derivatives. For this first one, I notice I've got 3 times something going to happen here. This is going to involve a chain rule. So it's going to be 3 cotangent inverse of 4x to the 3rd to the 2nd times the derivative of cotangent inverse of 4x to the 3rd. For this part, we're going to use the same method we used on the previous problems. We're going to start with y is equal to cotangent inverse of 4x to the 3rd, and that's going to then change to cotangent of y is equal to 4x to the 3rd. Taking the derivative, we get negative cosecant squared of y times y prime is equal to 12x squared. Y prime is going to be equal to 12x squared over negative, and I'm going to write this a little bit funny, cosecant y in parentheses squared. The reason I'm going to write this kind of funny is because I know something's going to happen when we do the triangle setup. Okay, so let's make our triangle. So we've got a y going on there, and that's an awesome triangle, by the way. No judgment from me. Cotangent of y is adjacent over opposite, so that would be 4x cubed over 1. The hypotenuse would be 4x cubed squared plus 1 inside of a square root. Okay, cosecant is the reciprocal of sine, so we're dealing with hypotenuse over opposite. So cosecant of y is equal to the square rooty thing, which is going to be 4x cubed squared plus 1. And then if I want cosecant squared of y, or cosecant of y squared, that's equal to just 4x cubed squared plus 1. So the derivative for this part is going to be 12x squared over 4x cubed squared plus 1. That means our final answer for this problem, that should be cosine inverse up there, 3 times cotangent inverse of 4x cubed squared times what we have down here, 12x squared over 4x to the third squared plus 1. That's a really pleasant derivative. Number 10, since we're doing the derivative first, we're going to start off with tangent of y is equal to 4x cubed minus 5 to the 4. Okay, I'm going to take the derivative of both sides. We get secant squared of y, and that's going to be equal to 4 times 4x cubed minus 5 to the third times the derivative of the inside, which is 12x squared. Okay, now I've got to figure out what secant squared is. And for that, I'm going to make a triangle. I also forgot my y prime. That's really important because we have y prime is equal to this lovely mess of a thing. I'm going to multiply those two together just to make this a little bit nicer. So 48x squared times the quantity 4x cubed minus 5 to the third power. And that's going to be over secant squared of y. All right, triangle up. By the way, this is going to be the last of these problems, and thankfully we can move on to some other things. Here we've got y. We know that tangent is opposite over adjacent, so we've got 4x to the third minus 5 to the fourth power. Adjacent is 1. That means that the hypotenuse is going to be the square root of 1 plus, and you're going to love this one, I'm going to do double parentheses going on here, 4x to the third minus 5 all to the fourth, all squared. Thank you, Mr. Butterworth, for this lovely problem. I totally blame you, and I hope that all of our students blame you too, because this is lots of stuff. That means that secant, which is hypotenuse over adjacent, is going to be the square root thing. Secant squared is going to be that thing with the square root gone, leaving us with y prime is equal to 48x squared times 4x to the third minus 5 all to the 3 over 1 plus the quantity, and this is going to be 4x cubed, I think, minus 5 to the fourth all squared. Isn't that beautiful? I think it's lovely. Okay, back to the world of no inverse trig. We're taking the derivative of the natural log of 2x to the fifth. The derivative of natural log of stuff is 1 over that stuff, so 2x to the fifth, and then times the derivative, I can't talk today apparently, times the derivative, not the derivative, of 2x to the fifth, which is going to be 10x to the fourth. The nice thing about natural log derivatives is that they can often be reduced. So when you stack this over that 2x to the 5, 10 over 2 is going to be 5. X to the 4 divided by x to the 5 is going to be x to the negative 1. So you can write this as 5 over x, which actually comes out really beautifully as a derivative of something that doesn't look so neat. The derivative of e to the stuff is going to be e to the stuff times the derivative of the stuff. Let's start out with e to the stuff, 5x to the fourth, and then the derivative of 5x to the fourth would be 20x to the third. And that's it for that one. How nice was that to have those two short problems after the very long, obnoxious ones we've been having. And I spoke too soon. We've got natural log of a quotient rule. I'm going to be kind of clever and use some log rules to make this a little bit easier. So I'm going to write this as y is equal to 5 natural log of 2x to the third minus 5 the natural log of x squared plus 3. I could even go a step further with the first one, but I'm not going to go there. I just didn't feel like doing a quotient rule. And if we're looking for y prime, we're going to have 5 times 1 over stuff, so 2x to the third. The derivative of that stuff is going to be 6x minus 5 times 1 over that stuff would be x squared plus 3. The derivative would be 2x for that. Okay, we're going to have 30 over 2 is going to be 15. X over x to the third is going to be over x squared. And then that's going to be minus 5 times 2 is 10. X over x squared plus 3. Not too bad. I could combine those, but I'm not going to. I guess I might as well do one as a quotient rule type thing. So we're talking about the derivative of natural log is 1 over stuff. In this case, that stuff would be 5x to the fifth over x to the 3 plus 5, all to the third power, times the derivative of the stuff. There's a quotient rule. So we've got the bottom x to the third plus 5 times, oh man, I forgot the 3. Oof. I'm going to back up a second here, because we've got to do a power rule before we can touch that quotient rule. So that's going to be 3 times 5x to the fifth over x to the third plus 5 squared. This is actually a little bit helpful for us. And then I can do my quotient rule. So we've got the bottom, x to the third plus 5 times the derivative of the top, which is going to be 25x to the fourth, running out of space here, minus the top, 5x to the 5 times the derivative of the bottom, 3x squared over x cubed plus 5 squared. Okay, we're going to play some fun math for a minute. The first thing I noticed is I've got this big fraction cubed and this big fraction, the same thing, squared. That means that the squared part can get rid of all but one of those things. The next thing I notice, I've got 1 over this fraction. So I'm going to rewrite that as its reciprocal, x cubed plus 5 over 5x to the fifth. My second part is just going to be times 3. My third part, the key here, is going to be we've got x to the third plus 5 squared, which means that can cancel with that. X to the, I can't cancel all of that. Where's my undo thing? There it is. I can just cancel out one of those pieces with the top of the first fraction, leaving me with a 1 up there. And I'm not going to simplify any of this stuff over here. We've got x to the third plus 5 times 25x to the fourth minus, I guess I'll simplify this, 15x to the seventh, which actually looks like it would cancel some stuff out, maybe. I don't know. But at that point, I'd probably call it a day. I'd like you to notice that if you had rewritten this as 3 natural log of 5x to the fifth minus 3 natural log of x to the third plus 5, that becomes a much less substantial derivative to take. Knowing log properties is a really helpful thing. Okay, 15, here we've got a product rule to start out with. I'm just going to kind of write this out. That's a really helpful thing. I know it's a product rule because I have two things being multiplied together. So we're going to do 5x squared minus 2 to the fourth times the derivative of the first. That's going to be 1 over 3x to the fourth multiplied by 12x to the third. And then that's going to be plus ln of 3x to the fourth multiplied by 5x squared minus 2 to the third times 10x. We have to remember those chain rules inside of those derivatives. It kind of would have been nice if I had written that out before the derivative step, but I'll deal with it. As far as things canceling out, I got an x to the 3 and an x to the 4. I've got a 12 and a 3, leaving me with just a 4 there. That would give me 4 times the quantity 5x squared minus 2 to the fourth. On this side, I'd probably put the 4 times 10x out front. So that'd be 40x times ln 3x to the fourth, and then times 5x squared minus 2 to the third power. Not a heck of a lot you can do. You might be able to factor some stuff out. I don't think it's worth it for trying to get any further because you're not going to get there. Okay, and then we've got number 16. This is another product rule. The first thing I'm going to do is to rewrite the first part, which is the cube root. Is 5x cubed plus 3 to the 1/3 power. And that's times e to the 4x squared. This one I will write out just to make sure we understand what we're doing. That's e to the 4x times the derivative of 5x to the third plus 3 to the 1/3 plus 5x to the third plus 3 to the 1/3 times the derivative of e to the 4x squared. Okay, first part, we've got e to the 4x, and the derivative of this is going to be 1/3 5x to the third plus 3 to the negative 2/3. And then here we're going to have, sorry, I forgot the chain rule for that, times 15x squared. And then we're going to have plus 5x to the third plus 3 to the 1/3 times the derivative of e to the stuff, which is e to the stuff, 4x squared, and then times the derivative of the stuff, which is going to be 8x. Again, not a heck of a lot that you can do here. You may have noticed that I forgot squareds on those e to the 4x's. I guess I could factor an e to the 4x squared out of both of these, and maybe there's stuff you can combine there. But with things that are this complex, likely you're not going to get much of a simplified answer. For number 17, we've got a quotient rule going on here. So this is going to be the bottom. And actually I'm going to rewrite this as this stuff to the 1/2 power. So 3x to the 5th plus 5 to the 1/2. The derivative at the top would be e to the stuff times the derivative of the stuff, which in this case is 3x squared, minus the top, e to the x to the 3. That's fun. And that's going to be times the derivative of this, which is 1/2. This is why I wrote this as a 1/2 power. 3x to the 5 plus 5 to the negative 1/2. And then times the derivative of the inside, which is going to be 15 x to the 4. That's over the bottom squared. Since that's a square root, it's just going to be 3x to the 5 plus 5. I'm not convinced that there's a heck of a lot you can do to simplify this. Although we certainly could, especially since we have some numbers in there. But I'm not going to go there. All right, for number 18, we've got a quotient rule involving some natural log stuff. So we're going to have the bottom. That's going to be 3x squared minus 4 to the 1/3 times the derivative of the top, which is going to be 1 over 2x to the 3 multiplied by, 6, not 3, x squared. And that's going to be minus the top, the natural log of 2x cubed times the derivative of the bottom. Bring the 1/3 out front. We're going to have 3x squared minus 4 to the negative 2/3, and then multiply that by the derivative of the inside, which is 6x. That's going to be all over the bottom squared, which is going to be 3x squared minus 4 to the 1/3 to the 2, which would be to the 2/3 power if you were so inclined. Okay, here we've got a derivative of a base other than e. Just as kind of a reminder, if we've got y equals a to the g of x, then the derivative of that would be a to the g of x, so a to the stuff, times the derivative of the stuff, and then multiplied by ln of a. What we're really doing is changing bases here, and all that we're doing that's different from e is multiplying by ln of that value, and that's going to convert that really to a base e, even though it doesn't look like it. So for this, we're looking at y prime is equal to 5 to the 4x to the 4 multiplied by 16x to the 3rd times the natural log of 5. And you're done. Kind of similar, in fact exactly similar to what we just did. If we're dealing with the derivative of a log of another base, what we're really doing is converting this to base e. So if I've got log base a of g of x, the derivative of this is going to be 1 over g of x, so 1 over the stuff, times the derivative of g of x, so times the derivative of the stuff. And then what we're going to do is divide by the natural log of whatever that base is. So ln of a, we tend to write that down there. If you want to write that at the end, that's okay too. So this would end up being 1 over 3x to the 4th times 12x to the 3rd, and then we're dividing this by ln of 2. I guess you could simplify this sum. That turns into 4, and we end up with just an x in the bottom. So we'd end up with 4 over ln of 2 times x. For 21, we've got the same type of problem we just had, but as part of a product rule. I see these two things are multiplied. So we've got the second, 4x to the 5th plus 5 times the derivative of the first, which is going to be 1 over 3x squared. I'm going to put my ln3 in the bottom right now. Multiplied by the derivative of the inside, which is going to be 6x. That cancels to 2, and my x's cancels to just x in the bottom. Then I'm going to have plus the first log base 3 of 3x squared times the derivative of the second, which is going to be 20x to the fourth. Not a heck of a lot else that you could do. I guess you could multiply this polynomial out front with the 2 up top. Still not going to make this much nicer. For 22, we're doing the same thing. We've got another product rule with two things being multiplied together. And we've got the second. So log base 2 of 5x squared times the derivative of the first, 3x squared, and then plus the first, x cubed plus 4, times the derivative of the second. And that's going to be 1 over 5x squared. We do times ln of 2 in the bottom there, and then times 10x for the derivative of the inside. 5 and 10 cancel, leave me with a 2. X and x squared cancel, leave me with an x. And once again, we don't have much else we can simplify here.